My name is Ken Brown. I'm from LCR Embedded Systems. I'm the Program and Applications Manager there at LCR Embedded Systems. Before I kind of get into my presentation, I do want to give a little nod to my predecessor. A lot of you might not know me because my predecessor, John Long, gave a lot of the presentations here at Tech Trends. A lot of you may have known him. He was a great mentor, a great boss. He always gave a very smart, informative presentation I think that everybody enjoyed. Unfortunately, he passed away last May. So hopefully I'll live up to his name a little bit since he always gave great presentations. So with that, we'll get started. Whenever we give these presentations at Tech Trends, we like to kind of give the perspective of a chassis manufacturer. I know there's a lot of different companies here that do a lot of different things. So we try to offer the perspective of LCR. What is LCR? We're a packaging company. We do electronics packaging. Most of our customers come to us with a unique requirement. We help them out. Sometimes we have to educate them. Sometimes they'll come and they haven't done VPX yet or aren't really familiar with it, and we kind of walk them through VPX, the pitfalls, the lessons learned, what works, what doesn't work. From a product perspective, just to show you what our perspective is, we do enclosures, we do electronics packaging, we do backplanes, enclosures, metalwork, the cooling, the I/O. We do this for the rack mount chassis. We do it for the Airing 404 enclosures, mostly for the open standards, the ATCAs, the VPXs, the VMEs, the COMEs. Who are we designing these for? Primarily, we're designing these for the mil-aero market, the Raytheons, the Boeings, the Northrop Grummons. These are custom enclosures where they bring us their unique requirements, and we design a solution that meets their needs. I don't know how many of you have heard this that have worked with these guys, but a lot of times they'll walk into my office or call me on the phone, and they'll say, I need COTS, and they'll go on for 20 minutes of all the reasons they can't use COTS. I'm not sure why they do this. Maybe there's a rumor there that if you start with this phrase, it's like a coupon for 10% off. I'm not sure why. What we are seeing these customers come to us with their unique requirements is that they like VPX. They like the form factor it's rugged, it can handle the I/O, it can handle the high speed. They seem to like it, so they usually come to us with maybe they'll just come with the CPU card they want to use and a few requirements of where they want it to go. We're also seeing that the majority of these new applications are going to put this system in an Airing 404 enclosure. And not only that, primarily it's going to be the 3U VPX. So for the purposes of keeping this presentation to a reasonable time, we're going to use that to frame this presentation, the 3U VPX in the Airing 404 enclosure. Primarily, I think one of the reasons that they like to go with VPX is the possibilities, the backplane. There's just a ton of I/O. It can handle a lot of high-speed I/O. From a system designer, from a backplane designer, from a user perspective, it offers so many options in what I/O can be brought out of the box. Whether it be through the newer RF or fiber optic I/O, differential pair signals, or just standard I/O. They have a lot of options of what they can do, and that's why they're drawn to the VPX. With those options come a ton of variety. From a system architect standpoint, VPX brings such a high quantity and high quality of I/O that I think it meets all their needs. There's virtually no limitations when you're trying to bring the I/O out of a VPX box. Is it too good to be true? From our perspective, a packaging house does rugged custom enclosures with VPX, and we find our customers liking that. They come knocking. We like that. They love the form factor. From a swap perspective, you could fit so much I/O, so much flexibility, so much performance in a small package. When you put it in the Airing 404 enclosure, you can create a sealed system that meets all the harsh environmental requirements. Conduction cooling, extremely rugged form factor that meets all the needs. With all those flexibility, with all that I/O, it sounds great. But I do want to say, too, there's other form factors that have brought various benefits to the table. We've seen VME, which is very rugged. It has conduction-cooled options. But from an I/O perspective, it doesn't necessarily give everybody everything they want. from a quality standpoint, from a quantity standpoint. It doesn't have the high-speed ability that some of the other form factors do. We've also seen ATCA pick up some popularity with some of our customers. Now, that will bring you a lot of the high-speed signals, a lot of the bandwidth, a lot of the I/O you need. But unfortunately, because of its size and the form factor of the blades, it's not so rugged. We have some very talented packaging engineers over at LCR, but I haven't seen them yet take the ATCA form factor and fit it in an Airing 404 enclosure, or in a pod for that matter, where it can handle that environment. Here you can see basically, so you have all those possibilities, you have all those choices. With that comes some challenges. There's a few enclosures I've shown you here of recent designs we've done. On the left, you can see they're using every conceivable connector and packaging it all in there about as tight as you can fit. In the middle, it's very basic. You just have power and a little bit of I/O coming out. And on the right, something a little bit more balanced, but again, some options there. Those top two connectors are actually some RF coax connectors and the circular connector. As well as the challenges of all the I/O you have, you can have some situations where things just aren't compatible. VPX is such an open standard. There's so many things you can do with it that sometimes there's just too many choices. This diagram here, we had a customer that came to us. He knew he needed about a 3-slot VPX system, but he hadn't quite nailed down which boards he wanted to use. So he sent us his 3 board options, and we took a look at them from a compatibility perspective. And unfortunately for him, because of some of the variations you can see, he more or less had to choose which one he was going to use before we started designing the system from a backplane design perspective, from an I/O design perspective. Not only this, do we see that these boards are the same functionality, but you have the difference. Even sometimes when a supplier will introduce the next generation of a board, we'll see some small differences in there that throw us a loop when they want to plug in the next generation. Add on to that, when you install this system in an Airing 404 enclosure, in the traditional sense, it does restrict your ability to access the backplane. There's not a whole lot of room in these boxes. There's not a whole lot of ways to go. You can get creative with some of your packaging schemes, but more or less, when you mount them in the traditional sense, the access to the backplane is not fantastic. So we want to maximize the possibilities we have here. We want to avoid a few things. We want to avoid high development costs. We want to avoid long development schedules, and we want to avoid a risky design. Through all this, there's a couple of things you have to be concerned about. What potential alternative cards could the customer be plugging in? What are the upgrade paths for their cards? You want to give the customer some options so that they want to upgrade someday. They don't have to replace their entire system. That's something they always want to avoid, and you want to help them with that problem. So there's a few factors to think about when you're designing your I/O possibilities. You want to offer a system that's flexible as far as the I/O. You want to offer good cost. You want to offer the schedule, performance, and you want to keep that risk down. From a performance standpoint, you don't just want to be concerned about electrical either. For the enclosures we design for our customers, mechanical performance is also important as well. Can those interconnects handle the extreme temperatures? Can they handle a vibration endurance, run through the mill standard 810? So for this presentation, I'm going to run through the few options we generally walk our customers through. There may be a few other kind of niche options that you can go with, but we find that majority of our applications we work with, this is one of the solutions we're going with to meet their needs. The first one we're going to review is what we consider the monolithic backplane and flex. Is basically your backplane, your I/O board, your I/O connectors. There's no interconnects. You can't separate them. It's a continuous piece, epoxy with the fiber coming out right to the connectors. From a performance standpoint, this is going to offer your best signal integrity. That comes with a cost. It's also going to probably be your most expensive option, particularly in the low volumes. And that's what us at LCR, we're dealing with the high mix, low volume, so that's something that we have to deal with on a regular basis. It also offers the least amount of flexibility. Unfortunately, with this option, with the great performance you get, if you make any changes along the way, you're probably going to have to replace your entire system. Along with that, with the flex, there's certain design skills, certain engineering skills when you design flex into a system to be concerned about to make sure that your company has those design skills. Another option in the flex area is what I'm calling the discrete backplane and flex. And basically, you have a separate piece of flex that joins your I/O area, whether it be a board or just an I/O panel, and your backplane. This does offer a step down in performance because of the additional interconnects. but it also offers a step down in cost. And with that, it also adds some flexibility. You have the potential, if you make some changes in your system, to replace any one of the three components to make those changes, rather than replacing the entire system. Again, you're still going to need those special design skills with a flex. And if you're not going to go with a rigid flex, you also have some manufacturing processes that need to be worked out, because there's some pitfalls there to avoid. Backplane cables. This is basically discrete cables, whether it be coax or twisted pair or just standard single wires. This is going to be your cheapest option. It's also going to take a hit in performance, though. You can get some cables that can do some of the higher speeds and some of the higher signal integrity options, but they're generally going to bump your cost up past where you want it, and they're going to be tough to fit in your design. This is going to be the least expensive. There's not a whole lot of setup. There's not a whole lot of tooling to build a cable. But unfortunately, with having humans build that cable, you get the inherent possibility of errors. With the flexes and the PCBs, you're always going to get the same product every time, so you don't really have to be concerned about human error on those. Depending on the amount of I/O you have, the number of wires, or how high the performance is on it, you get into the twisted pairs, the shielded wires, you can end up with a large, bulky cable bundle that's hard to fit in such a small form factor like this. And with that, you also need to secure those cables so that they can survive the environment we're trying to design for. The I/O, what we're calling the I/O transition board, basically this is where you have the I/O area on a PCB, and it plugs directly into the backplane. This option, we think, seems to strike a nice balance. It minimizes the interconnect, so you're going to get some decent signal integrity. If you hard mount the board to the front panel, you tend to have a very rugged design. You can also add all the supporting circuitry you need, whether it be filtering, ESD protection, or even signal processing. These are things we've all implemented on the I/O transition board. Your flexibility is limited, not as bad as maybe the Monolithic Flex, since you can just replace either the backplane or the I/O board and leave the other. It can be a little bit expensive depending on the performance of that PCB. If you're trying to still have the differential pairs and the impedance control, that board can get expensive, but if not, sometimes you can get away with some of those cost factors. When you hard mount that board to the front panel, it does give you the ruggedness, but then you're trying to blind mate that I/O board on while you're mechanically mounting to the chassis. There's some tolerance issues to be worried about there. LCR, we've implemented this a few times. This is probably our preferred option because of the balance it strikes of the pros and cons. We've worked out some of the tolerance issues, and we've successfully implemented it a few times now, so it's the way we tend to default to. A couple other options, the RTM I/O board. In a more traditional air-cooled system, this is a great option. You can plug those boards right into the RTM. You can grab a lot of the signals out of the RTM that way. With the right design, it can be rugged. You can also add the same supporting circuitry you add on the I/O transition board to this RTM board and get a lot of those features. Unfortunately, it can be expensive, and it's not just about the RTM board when you're talking about that cost. Obviously, that does add additional cost. If it's custom, it'll be even higher. But you also, if you were going to plug in an RTM board, you're going to have to do the whole card cage that supports those RTM boards, the rails, the card guides, the RTM VPX backplane connectors. You may still require cabling, depending on your system, to get the I/O from the panels of those RTMs to the outside world. And unfortunately, and most importantly for this particular discussion, when we're talking the Airing 404, you don't have access to the back of the backplane, really. In this traditional Airing 404 mounting scheme, as you can see here, it just doesn't fit within in the form factor. One last option is the VPX RTM cables. These seem to be becoming more popular. There's a few companies that make them now. And these are by far going to give you the most flexibility. With these cables, you can literally pull out any pin, any signal that's on the backplane by connecting to the RTM. We've also, in an attempt to implement these cables a few times, we've seen they're relatively expensive, relatively long lead times. You do have the cable management issues you have to deal with in such a tight space. And again, most importantly, you really don't have access to the RTM section. So from a form factor perspective, it's really not something we can implement. Back to our kind of our scale here, our 5-sided box. As you can see, all of these options, each one of them has pros and cons, depending on whether you're concerned mostly about cost or risk or performance or flexibility for the future. You have to consider all of these things when you're potentially choosing which I/O options you're going to use. Sometimes, when all is said and done, and you're reviewing your options, one option really doesn't sometimes meet your needs. You can see here, every now and then, you got to do somewhat of a hybrid approach. You can on your left, you can see this was an application we designed where we were plugging in FPGA cards. They had some SMA connectors, really low profile, right on the card. Ran some coax wires right to the front panel, and the rest of the I/O came in through a PCB, the I/O transition board, that plugged directly into the backplane. On the right, you can see an application where we combined some standard I/O cabling with a discrete flex. They needed some standard signals that didn't need the performance of a flex, and they had some signals that also needed the flex for the performance. We have a few general guidelines when we're talking to our customers that we walk through to help them make that decision, to guide them. You want to minimize connection points for signal integrity. Every time you add a connection point, your signal is going to degrade just a little bit more. Even the best interconnects in the world, you're still going to get some degradation in the signal. And then the other part of the argument is where you're talking about boards and flexes versus cable assemblies. The boards and flexes are going to be less error prone. Those are generally, once you've got the tooling and the setup correct and you've made a couple, they're going to come out the same every time. Cables are going to be a little bit more error prone. You're generally going to have people building these, and they are prone to errors. The boards and flexes are going to be more expensive in the low volumes versus the cables are going to be more expensive in the high volumes. Once you've got your tooling and you start running some, the prices decrease quickly with higher quantities for the boards and flexes. Whereas when you're having cable assemblies that are manually made, generally your costs are relatively flat regardless of how many you make. The boards and flexes are going to give you better performance. You can implement multiple layers. You can implement the shielding, the impedance control, differential pairs. You can get some cables that are going to give you that, but generally the flexes and PCBs are going to be a higher performance level. Boards and flexes are also going to be less flexible. When it comes to the cables, you can move pins, you can replace individual cables, individual conductors, but with the boards, it's kind of an all or nothing approach. To get the durability and the ruggedness that you need, generally you're going to hard mount something. That's the pro of that option. But you're generally going to have to deal with the tight tolerances there since you're now going to be blind mating your product.